We now look at equipotential surfaces or equipotential lines, but usually it should be a surface. So first let's do it for a smooth, parallel, uniform electric field. And then we take the case of a non-uniform electric field. So if we have two parallel plates and one is negative and one is positive, we will have a uniform electric field between them. And let's suppose that we start from point A and we go in the direction of the field to a point B, and the electric field is in the same direction. And then there's another point C over here, and then we'll see if we go from A to C what will happen. So we will look at the potential difference delta V between A and B, and the potential difference between A and C. Okay, and the electric field lines are all going like this. So this is going to be given by minus integral of E dot ds from A to B. And if this is our x-axis, which is the I direction, that's the y direction, then the electric field is going to be simply EI, and the ds is going to be dxi. I dot I is 1, so that can be taken out and just remains 1. The electric field is constant, so that can be taken out. And so this becomes minus E integral of dx from A to B, so that will simply become the distance AB. So let's write it as minus E times the distance AB, okay, where AB is the distance from A to B. Now let's find the potential difference between A and C. So if you're going along here from A to C, and then we have the same equation, integral from A to C, that was from B, that's up to C, E dot ds, and this will be minus A to C. E is going to be EI because the electric field is still in the x direction, and ds is in this direction, which and the angle between them is theta, and let's assume it's a straight line, so the theta will remain the same all along. So ds is going to be, well, let's say it's going to be dot ds for now, and then we can say that I dot ds is going to be the magnitude of I, the magnitude of ds, and cos theta, and the magnitude of I is 1, so it's simply ds cos theta. So this becomes I dot ds becomes ds cos theta, becomes minus integral of E ds cos theta from A to C. Now E is constant, so that comes out. Cos theta is constant, that comes out if this is a straight line. And we're left with the integral of ds. So when you integrate from here to here, that's this length, and let's call this length AC. So this will become minus E cos theta AC. So that's AC, and that's AB, that's theta. So AC cos theta is going to be the same as AB. So it's going to be minus E times AB. So we have exactly the same thing that we had before. So the electric potential at C, or A minus C, is the same as A minus B, and because delta VAB is V at B minus V at A, and delta VAC is V at C minus VA, and these two are equal, it means these two are equal, so VA is the same, that means VB equals VC. So the electric potential at these 2 points is the same, provided that they are on a line that's perpendicular to to the electric field, so that in that case only will AC be equal, AC cos theta will be equal to AB. If the point C is here, then AC cos theta will not be equal to AB. So it's true only if this angle is 90 degrees or this line is parallel to this wall. So the electric potential at C and B are equal, which means that it's same here, and we can move the point C anywhere along this line, which means that along this entire line the electric potential is constant, and that becomes a line of constant potential or same potential. Now, because this is two-dimensional, you have a plate here and a plate here, this will also be a surface, and that will be the equipotential surface. So if you have two plates, then at a given distance the potential will be the same all over the plate if the electric field remains uniform. So that's an equipotential surface. Now, if we go to a non-point source, a non-uniform source, so for, let's say, for a point charge, and here is our point charge, Q, then the electric potential at a distance r was found to be, as we found earlier, it's KQ over R. So if we take a distance r, some distance r1, let's say from here to here is r1, it will have some electric potential V1. And we take another point also at a distance r1, the potential here, if r is always r1, the potential here will be the same as potential here. So all points which are at the same distance from the charge will have the same potential. So we will get a circle in 2D, and we get a sphere, a spherical surface in 3D, which is an equipotential surface. It has the same potential everywhere because R is the same everywhere, and we just have one charge. Now if you go to another point which is at a bigger distance, R2, then if R2 is bigger, then this is smaller, but at every distance R2 we will have another equipotential surface. So that's another equipotential surface. So for every value of R we will have an equipotential surface. Now the electric field line here will be pointing outwards. Electric potential surface, equipotential surface will be like that, and they will be perpendicular to each other. So we will find that this is perpendicular to the equipotential surface. Now this is true for a simple point charge and no other charge nearby, but we'll find that even if there are other charges, this will hold. The potential has no direction, but the equipotential surface is a plane, so it should have some surface, some direction, and the electric field will be perpendicular to the surface. Now let's suppose that we have more than one charge. So let's suppose we have a positive charge here and a negative charge here. So the electric field lines will radiate outwards, and they will radiate inwards here, and they don't, if one going here and one going here, they will intersect, and they do not intersect. So what we get is a straight line here, and then we'll get electric field lines that go like this, and similarly on the lower side, and then they go out far away, and then they come here, and then they will go outwards like this, and these are all vectors, so they all have some direction. These will be coming in. Now if we draw the equipotential surface, which is supposed to be circular here, So we can draw concentric circles, but then we'll have concentric circles here, and a circle from here will intersect the circle from here, and we don't want intersections. Also, we want the electric potential to be always perpendicular to the field lines at every single point. So what happens is that we get an electric potential, equipotential surface here, and then another one which is like this, and as we get more and more, they can only squeeze up to here because there's going to be another coming from here. So it turns out that they get wider on the right side and they get wider on this side, and here they start squeezing together. So this will get further away and this will get further away on this side, and they will collect and get closer together. Okay, so they get closer and closer together here, and they move further and further away on the left two sides. At every point, the angle between them should be 90 degrees. Okay, it doesn't look right. The angle between the red line and the blue line must be 90 degrees at every single point of intersection. So that's you can check out some nice figures in the books. So these. Okay, so these red lines are the equipotential surface, or in this case they are equipotential lines, and the blue ones are the electric field lines. And for the parallel plates, we already had that figure, but we can show it again. So that's a plus and the minus. The electric field lines will go like this, and the equipotential surfaces will go perpendicular, so they'll go like this. Each of these lines would have the same potential. Now we can look at the relationship between the electric field and the electric potential, and we see one thing, that they're always perpendicular to each other at every single point. So if this is a potential V1, and along this line we have a potential V2, then because R1 is smaller than R2, this potential will be smaller than V1 because this is a positive charge. So the potential is decreasing this way, and that is also the direction of the electric field. So the electric field is in the direction, is in a direction of decreasing potential. So here we have positive and negative. So this is a higher potential, that's a lower potential. The electric field is going from the higher potential towards the lower potential. And if this were let's suppose we had 10 volts over here, so, and we assume that this is 0, then this is plus 10, then this is what could be like 2, 4, 6, 8 and 10 if they were equally spaced. Then this would be 2 volts, 6, 10 volts, 6 and 8, and then we reach the 10. So along this entire line the potential would be 4 volts because it's 4/10 of the total distance. So that's 10 centimeters and this is 4 centimeters, this would be 4 volts because it's a uniform electric field, so that the difference in each potential will be also the same distance. And the electric field is always going in the direction of decreasing V. So we can write the electric field as a delta V over delta X, or the rate of change of potential. And because electric field is in the direction of decreasing potential, it's minus delta V over delta X. Or we can write the electric field as minus partial V with respect to X. That will be the X component of the electric field. In this case there's only one component, but if it were a field like this over here, then the electric field going this way would have an x component and a y component, and we could say that the Ex is the partial derivative of the dv of the potential with respect to x, and Ey would be minus partial v with respect to y, and Ez would be minus partial v with respect to z. So the more rapidly the potential changes, the bigger the electric field. So here the potential is changing from one value to the other in this much distance, so the electric field is large. If we go here, the potential changes by from V1 to V2, it took this much space, but from V1 to V2 it's taking a much bigger distance. So here the dV by dx is smaller than here, so the electric field here will be smaller than here. So the electric field is large when the potential changes rapidly, which means that if the potential is constant, no change in potential, and in some conditions, then the electric field is zero, because then the derivative of potential is zero. So if we go along this line, then the electric field in this direction is zero. We do have it in this direction because the potential is changing in this direction, but in this direction there is no electric field. The electric field is perpendicular to this direction. And well, so we can also say that if you have a point charge which is positive, the electric field lines are going like this. The electric field lines are close together, so the electric field is stronger here and weaker here. If the electric field is strong, it means the potential changes rapidly, and so the potential for, suppose this is 100 volts and that's 90 volts, then the 80 volts will be a little bit further away, and the 70 volts will be even further away. Okay, so that's a 100, then 90, then 80, and 70, and the 60 would be even further away, because as the electric field gets weaker, the gradient of potential gets smaller and we get bigger distances. So this is 70, that's 60, and 50, and so on. And well, at infinity it will go to zero. So they have to get bigger and bigger. Now for a negative charge, the electric field lines are going inwards, and we still have the same thing. We will have, let's say, a minus 100 potential, and then we'll have the minus 90, and the minus 80 will be further away, and minus 70, and so on. They'll get further and further away.